Thank you for the introduction, and also thank you for the Institute for this opportunity to present my work. Actually, I have presented this work several times, but in a different continent. Anyway, I made some changes to this talk. I changed the title. I also changed some. Also include something new inside. So I guess this justifies me to give another presentation of basically the same things. So first, I would like to mention my motivation. Well, people have repeated these settings before, so I just skip them. First, we have a hierarchy of fragments of first order arithmetic. Actually, this hierarchy is established by several group of logicians. And we call that pigeonhole principle is the statement that there is no injection from any p plus 1 p. PA is first order arithmetic is also considered as some kind of finite access theory. So be formulated in PA. Here we consider this definable variant of pigeonhole principle. We call it a PHP of sigma n. That is, there is no sigma n injection from any b plus 1 to b. Last talk we mentioned we learned that PHP for sigma n is equivalent to b sigma n. This is done by. So this is one of my very this is one source of my very motivation. And another source of my motivation is from the study of kappa-like models by Richard K. Model of PA or a model of PA minus or a model of a model that includes some linear order is a kappa-like for some cardinal kappa. If the model is of cardinality kappa, if we fix any element in the model, then the initial segment decided by this element is of cardinality less than kappa. K proof. K try to introduce some. K try to axiommatize kappa-like models for different cardinal kappa. Prove that if M is kappa-like, then the full second order model over M second order cardinality scheme, meaning that there is no injection from M to things below some element. And if kappa is some living cardinal, then M is kappa-like if and only if this second order expansion of M satisfy what is called a generalized pigeonhole principle by K, meaning that for any element in M, we can find perhaps a bigger element in M. There's no injection from this bigger element into the smaller element. This is another line of my motivation. Actually, there's some development follow this principles introduced by K. K in a different paper, he proved that if kappa is any singular cardinal, any model of B sigma n plus failure of I sigma n, then we can find some carbon-like model that is elementary equivalent to this given model of B sigma n plus failure of I sigma n. We learned this from the QA's message talk. And if we tend to what is called I models, the Slayman showed that they for any n for positive n, we can find some omega left omega-like model of I sigma n plus the negation of B sigma n plus 1. So I sigma n plus generalized pigeonhole principle does not imply B sigma n plus 1. So of course, by case result, we learned that B sigma n plus the negation of I sigma n implies generalized pigeonhole principle. I mean, generalized pigeonhole principle for all first order definable maps. So a way to, so of course, the theorem of Slayman is not as strong as case theorem. Actually, it is optimal because we cannot achieve results similar to case theorem for I models. The Slayman theorem, I guess Slayman perhaps never has not published his proof yet, I guess. I only learned this on talk given by Slayman on open source birthday party. But actually, then after this proof, there is some development of so-called flexible formula, and it was something first proved by Wooding and then generalized by Frank and Anayat. Using flexible formula, we can give another proof of Slayman's theorem. This proof, if you look after the joint paper of Frank and Anayat, then it's easy for you to come up with a proof of this. This is another line of motivation of my work. So actually, in case second paper, we also raised a question concerning the variance of pigeonhole principle he introduced. Because the card is the first order part of the second order coordinated scheme. GPHP is the first order part of its generalized pigeonhole principle. And we can also restrict card or GPHP to certain definable functions in certain class of formulas. Of course, it's easy to see that generalized pigeonhole principle is stronger than coordinated scheme, but the reverse direction is today still unknown. This talk, I will present something related to this question, but not a full solution to this question. So there is another line of motivation. This justifies me giving this talk on a workshop connected to reverse mesh. So it's that the variance of pigeonhole principle proposed by K has this specific family, or we mentioned that we call them card, and card has proved quite useful in reverse mathematics if we want to learn something about the first order theory of some principles. For example, it's by Gaussian and Slayman, also by K. combinatoric scheme for sigma n plus 1 maps is not provable in I sigma n. And on the other hand, Cornelis and Slayman, they use this combinatoric scheme to show that the so-called Reinbold-Ramsey theorem for pairs is not arithmetically conservative over RCA 0 because this Reinbold-Ramsey theorem for pairs implies this combinatoric scheme for sigma 0 2 definable maps. This instance of coordinated scheme is not provable in RCA 0. This is an example how pigeonhole principles could relate to and there is another variant which look quite like a pigeonhole principle or case generalized pigeonhole principle. We call it weak pigeonhole principle, saying that there is no injection from any 2 to x if x is positive. Clearly, this weak version of pigeonhole principle is stronger than generalized PHP. And it is also interesting to note that weak pigeonhole principle for delta 0 map actually is extensively studied in bounding arithmetic and proof complexity. Also in complexity theory. So we're interested in this weak version of pigeonhole principle because it's related to some analysis of dominated convergence theorem. This variant of convergence theorem is introduced by Abiga and Root. This theorem states this statement says that suppose we have a function f and we have a sequence of function fn, and we have another function g, and all of them are measurable and defined on the unit interval. And suppose this sequence of fn is dominated by the function g and converge almost everywhere to f. And the integral of fn converge to the integral of f. This is so-called DCT prime by Abiga. And this is related to the people call 2WWKL, meaning that every pi 2 set in Cantor space with positive measure is non-empty. Also related to the existence of two random real. So Abiga and Root show that over RCA 0, this DCT prime and 2 WWKL and 2 random, but together with the B sigma 2, they are all equivalent. And so the first order theory, they also show that the first order theory of this version of dominated convergence theorem is exactly axiomatized by B sigma 02. Of course, then from this theorem, it's natural to raise the question whether we can remove this B sigma 2 in this equivalence. It turns out that we cannot remove this B sigma 2. However, so the question is kind of whether 2 WWKL and 2 RAN can be separated. This separation cannot happen in standard models because of theorem of Kuchera on randomness. So this is an instance of Kuchera's theorem that if X is multi-loop random relative to the Hoti problem, then every delta 2, every pi2 set of positive measure contain an element which has infinite tail on this, which has infinite tail being this full-length WX. So that means in standard model, we cannot separate 2 WWKL and 2 length. So later we work with logicians in Singapore, and we finally able to separate this 2 length and 2 WWKL. To do so, we introduce some intermediate statement, what we call 2 WWKL of 1/2, meaning that every delta 2, every pi2 positive set with measure at least 1/2 is non-empty. And of course, this implies 2 length easily. And then we show that the first order theory of this 2 WWKL is actually axiomatized by I sigma 1 together with weak pigeonhole principle for sigma 0 to definable maps. And then we also show that, so recall that if we don't have this restriction of 1/2, then 2 WWKL has its first order theory axiomatized by B sigma 2, right? So this is axiomatized by WPHP for sigma 2 map. And of course, we want to know that whether B sigma 2 and this WPHP for sigma 2 maps are equivalent, and it turns out that they are actually not equivalent. So B sigma 2 is strictly stronger than weak pigeonhole principle for maps, and this weak pigeonhole principle for sigma 2 maps is stronger than cardinality scheme for sigma 2 maps. So then we have a separation. 2 length and 2 WWKL are actually not equivalent. 2 length is strictly weaker than 2 WWKL. This is another source of my motivation. So now, motivated by all these works, I want to introduce some other variants of pigeonhole principle, of actually finite combinatoric principles. We call WPHP is no injection from 2x to x. Generalized PHP is for any A there is B, then there is no injection from B to A. And we may also consider finite Ramsey's theorem. We may also introduce the definable variance of finite Ramsey's theorems in this way. So for example, we have a FRT EK of gamma saying that for any A, we can find some B, such that for any coloring in the class gamma of length E tuples from B with K colors, then we can find some homogeneous set of size A. Of course, we have this. We have the version for arbitrarily many colors, and we have the version for arbitrarily long tuples. And if we regard this finite Ramsey theorem as a two-player game, and the first player presents some coloring, and the second player is asked to present some homogeneous set. And in this formulation, we may find that it is a little unfair for the second player, because the first player does not need to present a finite map. He just needs to present a definable map. But the second player is asked to present some finite set. So this lead me to this fair version of theorem. So in this final version, we only ask the second player to present some definable homogeneous set. But then we have a question about how to say something about the size of the definable set. We require that the size of this definable set must have definable cardinality at least A, meaning that there is that for this homogeneous set, we must be able to find some, but this should be gamma, sorry, this should be gamma. We must be able to find some gamma injection from A to this fair version. Actually, the fair version at the first look, it seems a little artificial, but it turned out to have some interesting properties. Yes, it is homogeneous. And
what is F minus 1 over
I? This should be C, I guess. Sorry, this should be C. Some typos. This should be C. And this is F. This is F. So in this color, if we fix a color I, then the image of this color has cardinality.
So, but this pre-image is
it's
a set
not
sequences.
It's not a set in the model. It is only definable. It's a set only in definable sense. Yes. Okay. On the board. Okay. Yes. Yeah, there should be something like this.
I know if you don't want to do it. Write C minus 1 y.
Sorry. Yes, you are right. You are. Yeah, this formulation is yes. This formulation is. Thank you. Yes, this formulation is problematic. Yes, I see. If C is that of there is there's an injection from this. And there's a color. There's a color I. Yes. Should be something like this. Sorry. Thank you for the for this correction. This is the fair version. Actually, it's quite. I think it's quite interesting. Later, I will mention some question. I guess is worth looking at. So we have some easy relations between this version, this definable variance of finite combinatorial principles, and all of them are quite easy to show. For example, that if we increase the length of tuples, then of course the strength of RT increase. For example, we also have this fair version for. Well, this is also easy to see. The fair version of FRT 1 is just a kind of a strengthening of a generalized principle, right? Because in this, we require that for any map from this larger B to A, it cannot be an injection. Then there must be 2 points that have same value. But of course, this fair FRT for one element is much stronger. All of these are easy to see, and all of these definable version of combinatorial principles are actually weaker than B sigma n plus 1, because if we have B sigma n plus 1, then any definable maps like this become finite maps. So then we can apply finite combinatorics inside the model. And then we also have some equivalence, maybe not quite obvious, that generalized Peirce principle for sigma n plus 1 that is equivalent to FRT1 for sigma n plus 1, equivalent to FRT1 with 2 colors for sigma n plus 1, and equivalent to fair FRT1. The proofs for this are not hard but tedious. I'm going to mention the proofs. And then, of course, from this, there's we may naturally raise a question. So how about fair FRT1 for two colors? So it turns out that if we only use 2 colors of this FRT, fair FRT1, then it's weaker than we remove the number of colors. This version is provable in I sigma n. So the proof is, I guess I may skip this. But the proof, quickly go through this proof. So it's non-uniform. We have to discuss 2 cases. One case is we have this GPHP for sigma n plus 1. And it's already on the previous slide. And the other situation is that we don't have a GPHP for sigma n plus 1 map, but we have I sigma n. Then we can find, we look at this cut. This cut is that this cut is something like GPHP whole for this element A. If GPHP whole for this element A, then we collect this all such element A, then we get a cut. And it's interesting well, we can easily notice that this cut is actually an additive cut, meaning that for any A in this cut, 2 of A is also in this cut. So then we want to show that fair FRT1 2 is true in such a model. So we fix the coloring, and then we want to find some homogeneous set for this coloring of size, for example, at least A. So we use a little story of I sigma n, and we can find that. So this is a partition of element below B, and we can so the partition could be very wide, but anyway we can collapse each part into a plot initial segment of M. It may not be a cut, but it's something like a cut, but may have some maximal element. So we compare these 2 cuts to this cut I. So if one of the cut is longer than I, if one of these cuts is longer than I, then we can easily find that this cut, one of these Ji is longer than I. Then we can easily find that we can easily find an injection from A to this Ji. And And together with this collapsing map, we get a kind of a homogeneous set. And the second situation is both ji equal to I. Then it's also easy to produce projection from B to I. Then we get this. And there's another possibility, but that would never happen. So this is the fair FRT 1-2 in I sigma n. Later we will find this is quite interesting. Now I'm going to move to fragments of CAD and GPHP. So recall that we mentioned the question of K, whether GPHP, the first order scheme of GPHP is equivalent to the first order scheme of cardinality. But we don't know the answer. However, if we only consider fragments of these two schemes, then we can show that actually CAD is weaker than GPHP. So the plan to show this is like this. We begin with a countable model of inside this model we have I sigma n, but we don't have sigma n plus 1 cardinality scheme. So of course in such a model we can find a counterexample to this card scheme, for example F0. And we want our plan is eventually we'll get a model M, which is a model of a cardinality scheme. So we want to kill somehow defeat this counterexample to CAD. How do we do so? The idea is that we add some new element into the model, to the ground model M0, so that this sigma n plus 1 injection become undefinable on this new element. So that means this F0 can no longer serve as a counterexample in the final model. So this is one part of the story. And the other part is that we also want to keep, of course, if we don't have a CAD in M0, we don't have GPHP in M0. But we want to keep, in the final model, we also want to keep GPHP fail in the final model. So the idea is that we take a very long initial segment of M0 and we keep this initial segment unchanged. So we add some new element to the model, but we don't want to bring any change to this initial segment. So that means we have this failure of CAD. And of course, it is also a failure of GPHP if we only look at this initial segment. Since we don't change this initial segment, then in the final model, we still have a failure of GPHP at this initial segment. So this is the idea. Then we iterate, then we defeat all counterexample to CAD and we keep longer and longer failure of GPHP. This is the idea. Of course, for this iteration, we need to learn two things. The one is that how do we add the C0? And the other is after one step of iteration, we get a new model M1. And to be able to iterate over M1, we need that this M1 also has failure of CAD inside, right? We kill a counterexample to CAD, but we don't want to kill CAD at one step. We still we don't want to defeat all counterexample at one step. We still want that in this new model there is some counterexample to CAD. So for the first, how do we get this C0? We use some construction by Paris. So he called Paris introduced this construction when he proved. Actually, there are two proofs of the pi n plus 1 conservation of b sigma n plus 1 over I sigma n. One is given by Harvey Friedman. Paris proof he introduced an power construction. The construction is like this. We take any non-standard model of I sigma n and take non-standard element, say A, in this model. Then we take an ultra filter of the Boolean algebra of m finite subsets of inner cell sigma decided by A. And then we take all the equivalent classes of m finite functions with domain being A. And this gives us a new model N. And this new model will be a cofinal extension of the ground model, and it will also be a sigma n plus 1 extension of the ground model. So this is the Paris construction. But we like to view Paris construction, ultra power construction in another way. And actually, ultra filters actually are, in many cases, ultra filters are just types. So this ultra filter U can be regarded as a type with a bounding element. It's a type about something below A over M. So then, of course, we can take some sufficiently saturated model containing M. And there is some realization of this type. And we take this, pick this realization, then the above model N is just isomorphic to the following model. The following model is we have this M finite function with domain being A. Then we calculate the value of f of C. C is something outside M, but in the monster model. Of course, F and C are both in the monster model. So we can calculate the value of F and C. And we collect all these values and we get this new model, M of C. It's isomorphic to N. This is easier, at least for me, to visualize this M of C. It's just like building an extension ring over some ground ring. So this is the first idea that we need. And the second idea is what I call a lifting lemma. So now we know how to add the new element C to a ground model M. So recall that we want that after adding this new element, we still don't have cardinality scheme in new model. This depends on the following observation. I call it a lifting lemma. So suppose we have a model used in Paris construction. It's a model of I sigma n. And suppose there is some sigma n plus 1 injection in this model to some element in from the whole model to some element in M. Then we build this Paris construction, so it is something like M of C. Then we can show that actually in this model there is still an injection, sigma n plus 1 injection from the whole new model into this small element A. Of course, this injection is a little different from the original one. But this lifting lemma basically says that if we have failure of cardinality scheme at the ground model, then we still have failure of cardinality scheme in the ultra power extension. This is what we need, and the proof is just use the idea that this ultra power model is something of this form. So if we have something of this form, then it's not hard to imagine how we define such an injection, because every element in this new model can be identified with such a function, right? And if such a function is in M, then in M there is an injection sending this, given this function M, some index below A. So then we can we can just lift this indexing to the new model. So this is the idea. But of course, then there is some subtlety to take care about because in the new model M of C, we don't know which functions are M finite and which are not. There could be some new finite function with the same domain A, and then we don't know about this. Then this can be done using elementarity between M and C. So with this lifting, then we can carry out our plan. So we start with some model of I sigma n and the failure of identity for sigma n. Then we take a cofinal sequence bk in this. Then we build a sequence of models. Start with this M. Then we add some new element into M. Model. Of course, we need that this new element. We also require that this new element would defeat some counterexample to defeating the counterexample to the scheme. And we also keep longer and longer initial segments of the model unchanged, so that in the previous model we have an injection from this long initial segment into the short initial segment A, and we keep these initial segments growing. So that means we keep finally we can keep the failure of GPHP. This is the idea. This is just the last one is just given by the lifting lemma. Finally, we take the union of the chain, which model as we want. This is the first separation. And then I would like to move to FRT and so this is also some, I guess, expected separation that FRT for sigma n plus 1 together do not imply weak general principle for sigma n plus 1. But the plan is to begin with M0 as above, and if we see a counterexample to FRT in M0, then we just like before, we add some new element to the model so that we made this counterexample no longer a counterexample. Because being a counterexample, it must be a total map. And this new element making the counterexample being partial, then no longer be a counterexample. At the same time, we keep a long initial segment of the model unchanged. This is for keeping the failure of WPHP. Because if we have a failure of WPHP, then this failure can be seen in the initial segment, because it is so there is some sigma n plus 1 map from 2 times A to A, right? If we keep a 2 times A unchanged, this counterexample is still a counterexample in the final model. So this is the idea. Of course, to carry out the idea, for example, how do we add some new element to the model and keeping this unchanged? Then we need some lemma. So this lemma basically say that if we choose y that is large enough, suppose this formula defines some sigma n plus 1 carry on E tuples from y, and this y is sufficiently large, then we can add some new element below y. The data, and then we can add some new element into the model. So there are two cases. Either in the ground model we can already find some homogeneous set, or we can add some new element, making this coloring being partial in the new model. Technical, I guess. I'm going to read all the details out. Oh, this A is a witness of the failure of. Yes, I see. Yes, this A is a witness of the failure of the weak pigeonhole principle. Okay, this X is that we want to find some homogeneous set of size X.
Okay.
So this in the first case we have a homogeneous set of size X. The second case we can defeat the counter example. So how do we choose Y? Then perhaps this calculation just give you a little taste about how we just using finite combinatorics. We have this primitive recursive function of calculating Ramsey numbers. Then we just iterate it to non-standard many times. This ensures that we can, if we need, we can do some we can achieve this one. We can achieve that we can find some tuple that making this map being partial. At the same time, we do not add some new element. This story behind this. So I guess this is something I put in my previous presentation. So there is another family of fragments of is recent year people have found more and more connection between this family of and between these fragments of reverse mass, in particular the first order theory of theorem for pair or P sigma n. This we need a notion of approximation to a partial function. So an approximation of length b to a partial sigma n definable function is a sequence such that if we look at this partial function, look at the value of this partial function on the first element, on elements below the first element of this sequence, then we find that all these values are bounded by the second element of the sequence, and so on. We have such a sequence is called an approximation. And B sigma n is the sigma n plus 2 sentence saying that for any such partial function, we can always find an approximation of arbitrary fixed length. So it's known that P sigma n is between I sigma n plus 1 and I sigma n. Actually, of course, P sigma n plus 1 is also between I sigma n and I sigma n plus 1. But actually, P sigma n is P sigma n and P sigma n plus 1 are dependent over I sigma n. And together, they are still weaker than I sigma n plus 1. So the construction for this irreversibility of I sigma of this arrow is very similar to the construction of B model mentioned by before. We just iterate this construction of B model for omega many times, then we get a model. Then we reach a model of these two principles, but we don't have I sigma. This is P sigma n. Of course, we would like to learn all these variants of FRT and pigeonhole principles, how they are related to this P sigma n. This is for this we use result from some unfinished project of me and that if M is a model of I sigma n is a confined node and sigma n plus 1, then the situation of the truth of P sigma n does not change between these two models. Actually, I sent this the draft of the results in this talk to Tim Wang, and he told me that recently he and Meng Zhou discovered a stronger form of the. So then, combining this result and also the implication from P sigma n to P sigma n plus 1, also the construction of models for with pigeonhole principle but not P sigma, and also can combine the construction of variance of FRT here, we can finally get a model which satisfies P sigma n and WPHP. Actually, so this is results, and I would like to mention some questions. That may seem interesting. So here I present some definable variants of finite combinatorial principles. Finite-Ramsey theorem. Of course, you may wonder. People may try to formulate other finite combinatorial principles, or for example, the HJ theorem or Turing's theorem in similar way. Then I guess we can obtain some similar results. Then the question is, how about the relation between these definable for example, we have definable FRT 2, for example, and then we have definable FRT 3, for example. Of course, definable FRT 3 implies definable FRT 2. But is it reversible? I don't know about this. Family of questions. And there's another family of questions. So I mentioned this that the first order theory of 2 WWKL 1/2 is axiomatized by with pigeonhole principle for sigma 2 maps. And we also learned that this variant of WWKL implies 2 rank. So how about 2 rank and for example GPHP we study here, for example, as 2 rank implies GPHP for sigma 2 maps. And there's another question which made me think that fair FRT is interesting. So this is related to the first order theory of RT22, which is I guess a big open question in reverse mesh of so we learned this series of results concerning the first order theory of RT22, and there are 2 recent ones that RT22 is pi 1 conservative over P sigma 2 together with the well-foundedness of epsilon 0, and also over P sigma 2 together with the well-foundedness of this omega to omega sub n, which is the power of omega to omega. Only for standard n. So they also show that RT22 is pi04 conservative over. So we learned previously we learned that if we have this fair FRT12 for sigma 3 definable maps, it's provable in I sigma 2. Actually, I don't know whether it is provable in B sigma 2. So we may ask whether it is provable in B sigma 2. But suppose it's not provable in B sigma 2, then maybe we may try to add RT22 into the theory, and we may also try to consider whether this can be provable in RT22. So this is apparently it seems I personally guess the answer to the first question is positive because we have case Aleph omega like model of B sigma n plus the failure of I sigma n. So in this in such a model, for example, we consider means this n is so we have kind of this cardinals in kind of not the faithful picture, but it's something like this. So suppose we have some A here, and suppose we have some definable map of on some B here, which is definable. Then we by cardinality cardinal arithmetic we learn that if this is a map from B to A, for example sigma 3, then of course we learn by cardinality by cardinal arithmetic we learn that the sum of this cardinality greater than n, right? However, this is only from outside the model. But inside the model, if we learn this, we know the existence of this I, can we build some injection from A to the pre-image of seems not quite easy to do so because in this model we only have, for example, B sigma this. We don't have. We don't have I sigma 1. So if we want to build some injection from A to this pre-image, then we can kind of enumerate a part of, we kind of being able to order a part of this pre-image. And that means we have something very similar to, I don't know, some induction principle, etc. However, we don't have this ability in this is why I think this FRT12 is interesting for me because I cannot solve this. This is my talk. Thank you. I forgot. Thank you.